So in this video, I'm going to show you how to load and display an image created by KOALA Painter in assembly language on the Commodore 64. The KOALA Pad was a very popular graphics tablet used by digital artists in the early 80s, and it came with this cool program, KOALA Painter. We're going to take a really quick tour of KOALA Painter to see how it loads and stores images. Then we're going to talk about the VIC chip and how it can display a multicolor graphic on a Commodore 64. And then we're going to put together a program in assembly language to load and display one of these pictures. The Commodore 64 I'll be using has just one disk drive and no KOALA Pad. This version of the KOALA Painter doesn't need a KOALA Pad, just uses a joystick. So when you fire this up, you got to first pick the language English, and you're brought to this main menu. I'm going to change the disk in the disk drive to a disk I found on the internet that was filled with KOALA images. There's a link in the description of the video where you'll find several disks of images that you can use to test this out. Or if you're actually a good artist, you can create your own. I am definitely not a good artist, so I will definitely rely on pre-created art. All right, now that I've placed a disk in a drive, you'll move the pointer over to storage and you'll tap the button. And here it's going to show you what's on the disk. It's kind of interesting how the disk is laid out. So it shows that each disk can hold about 16 pictures, lettered A through P, sort of. So we'll just pick some of these at random to see what they look like. So we're going to choose, I don't know, KOALA. And then the way you choose it is you click on Get first, and then you drag Get over to this word KOALA, and then you press the button again. And then it's going to load the picture into memory. All right, now the picture's loaded into memory. So if you move the pointer off the screen and you click the button, it brings you back to the main menu. If you move the pointer again off the screen and click a button, it pulls you into the image. And there's a nice image of a koala holding a KOALA pad. So let's take a quick look at how these images are stored on the disk. So we're going to reset our computer and take a look at the directory. So the file names are stored in a kind of an annoying format. The first character is the Commodore 1 key when you're in quoted mode, followed by the letters PIC space and a letter, and then the name of the picture padded out with spaces to about 14 characters. We're going to rename these files to a much simpler file name so it's easier for us to deal with. So make a copy of this disk, and then for each file you can rename it with a command like this. Open 15, 15, or a colon for rename the new name, Ferrari for example. Then you press Commodore 1, so you get that little inverted spade character. Pick space N space FEEARI space, and then you just close 15. That will rename the file. And of course, I will rename all of these. And here's what the disk looks like after I've renamed them all. Excellent. These will be much easier to deal with when we're testing this out in our program in assembly language. Well, before we get on to writing code to read these files in, let's take a quick detour and talk about how the Commodore 64 multicolor high-res video mode actually works. Right? A picture on the screen in multicolor mode is 160 pixels across and 200 rows down. Each pixel is stored in 2 bits, where there's 4 colors defined for each pixel. Sort of. We'll get into that in a moment. There are 160 pixels across that are 2 bits wide, so that gives you 320 across. If you multiply that by 200 rows, you get 64,000 bits. If you divide that by 8 to get the number of bytes, you'll see that the pixel data for a screen takes up 8,000 bytes. Within 2 bits, you have 4 different possible combinations. You have 00, 01, 10, and 11. Each one of those combinations will choose a color from 3 different color palettes, or the background color. So of course 00 is the background color, which is the color of the screen. 01 and 10 refer to what's called matrix color memory. Matrix color memory is a 1000 byte area of memory where within each 8x8 pixel block on the screen you can have 2 different colors defined. Color 1 is in the top 4 bits, and that's 16 different colors you can choose from. And color 2 is another possibility of one of 16 colors to choose from. So the color combination 11 for color RAM works exactly like matrix RAM, except it's in a different 1000 byte block of memory called color RAM. However, in that block of memory, there's only 4 bits to choose one of 16 colors. So where in memory do these 3 regions need to be for the VIC chip to see them? Well, the VIC chip can only actually see 16K of the 64K that's in the Commodore 64 at a time. When you turn on your Commodore 64, it is configured to look at bank 0. That's addresses 0 through 3FFF. For the purposes of this video, we're going to point the VIC chip at bank 1, which is 4000 through 7FFF. For the most part, the VIC chip is divided into 1K segments. For the pixel data, however, we have a choice of either the first 8K of the bank or the second 8K of the bank. We're going to choose the 8K that's in the second part of the bank for this video. That leaves us 8 1K blocks in a first bank. We need to pick one of these blocks for our matrix colors. We're just going to put it right before the pixel data at address 5C00, and that leaves the other 7K of the VIC2 chip available for other things like custom characters and sprites, things that we're not going to use in this video. The 1000 byte region of color RAM is always located at D800 and is not within the 16K window of the VIC2 chip. So with everything we've talked about, the file format should come as no surprise at all. The file is stored as a PRG file program, and the first 2 bytes of the file is the memory address that it loads into by default, which is address 6000, which of course is the upper 8K of VIC bank 1. Next in the file is 8000 bytes of pixel data, followed by 1000 bytes of the matrix color data, followed by 1000 bytes of the color RAM data, and finally 1 byte for the screen color. You add those all up together, you get 10,003 bytes. If you divide that by 256, you get 40 blocks. So each file on a disk is 40 blocks. All right, let's fire up an assembler and let's write some code. We are going to write this program using the Laser Genius Assembler by Ocean Software. To start it up, you just type in load gen ASM, 8,1. There is a link to the software in the description of this video if you wish to follow along with it. If you were back in 1986 and you had a Commodore 64 and a single disk drive, which I believe was the most common setup, at least amongst my peers, this was a great assembler. What makes an assembler a good assembler back then? You want flexibility. So the fact that the assembler can reside in 2 options of memory here, you can have it either in low memory or in high memory, was great because depending on what you're writing and where you're storing your graphic assets or sound assets or libraries like your music player in memory, you want to be able to move the assembler around so you can write the code and test it properly. And that you can move the location of where the source code is stored in memory, and you can pretty much put it anywhere where the assembler is not. So you can really kind of play that little Tetris game of where to put things in memory as you're building your project. So if you take a look at the memory map that I'm showing here on the screen, this is the kind of layout that we're going to go for our project. This is not the only layout you could possibly use. You have lots of different options and you can move things around wherever you want. It's really the only static place in memory we need to worry about at the moment is where the full image data is going to be, because that is the memory location of VIC bank 1, that 16K window. And in that region of memory is our matrix memory, which we decided to put a 5C00 right up to 7FFF, and the 8000 bytes needed for the pixel data. Now you'll notice that I included more memory than that. That's because when we load the file to memory, it's going to load into the pixel data memory, plus it's going to spill over with its matrix memory and color memory. So we need to have a little extra wiggle room for that. I think if we use the high memory for the assembler, moving the assembler to underneath the basic ROM, we can then put our object code around 3000 to, I wrote 3100, but it's probably even less than that. We don't need a lot of room for our compiled code. And then it leaves us plenty of room for the source code in memory to be at the very beginning of RAM, around 800 to 2FFF. So we're going to choose the high memory option. Now that the software is loaded, you can see that it's version 1.5H. That H means we're using the high memory version. It would be an L if we chose the L memory version of it. So it's starting a new project, so it's clearing out memory. That part's fine. And now we have this question of text memory. Here you tell it where you want the source code. If you press enter by default, it'll just take all of the rest of memory. But we want to do that. We want to use the window of 800. You put a comma, 2FFF. So now we've configured the assembler and the source code regions of memory. So now that we have the assembler loaded into memory, we can take out the assembler disk. We don't need it anymore. And we can put in our modified picture disk. So let's do that. So now with the disk in the drive, we're going to use commands similar to the DOS wedge to deal with it. So for example, @$ will give us a directory. And if you're not familiar with the DOS wedge, that's okay. So Laser Genius uses an editor similar to the basic editor. So there's line numbers involved. So we're first going to turn on automatic line numbering with the phrase auto 10. 10 means it'll count by tens. So we'll start with line 10. And the first thing I'm going to do is introduce a comment. Comments, of course, start with a semicolon. And we're going to put an @pic.s. This defines the file name of the source code we are working with. So later when we save it, we can just use the up arrow key to save it instead of trying to remember the file name. That's really useful when you have multi-file projects, and it ensures that you don't accidentally save a file on top of a different one. We're going to use the .org sudo operand to define the memory address of where this program will be assembled to, which will be 3000 hex. And then we'll start with a comment. You don't have a lot of room for comments in Ledger Assembler, about 16 characters. So we'll just kind of put 16 characters here. And then this program is going to show a KOALA pic. Then we'll put this here. Now, the way I like to approach writing a program is I kind of lay out the different steps that I want the program to take. And I do that by creating fake routines that don't do anything yet. So I'm imagining I'm going to want a routine that's going to load the file to memory. So I'm going to jump to subroutine load file to memory. I'm going to imagine that it comes back and the file's in memory. I'm probably going to want to configure the VIC chip to put it into graphics mode. In multi-graphics mode, it'll probably have the picture in black and white at that point because the color memory is not quite in position. So then I would probably want to copy colors to move the color information into position, move the matrix memory into the VIC 16K window, and then move the color memory to where the actual color memory is on the computer. I'm going to then JSR to a wait key so the user can look at the picture and press a key. And then we're going to jump to a subroutine to restore the VIC back to normal. Then we'll RTS to exit the program. So this is kind of our initial code here. Now those routines don't actually exist yet. So if I were to assemble this, the assembly would fail. So what I usually do next is I create what I call the to-do section. And this will be stubs for these routines that don't actually do anything. So for example, we'll create a load file routine, and all it's going to do is return from subroutine. It's not going to do anything. Then we're going to create a config VIC, which will also RTS, a copy colors, which will RTS, a wait key, which will RTS, and a restore VIC that will also RTS. All right. So we're going to press enter to exit, enter new lines of source code. So at this point in time, we have a program that does nothing. Now, what's neat about Ledger Genius is as you type this stuff in, it looks kind of sort of formatted, but not really. If I were to list the program now, you'll see that it's actually formatting the code and storing it in this condensed format in memory. So you can see the first column has our labels, this middle column has the mnemonics, and the right column has our operands. But at this point, our program should compile, and we type ASM to see if it assembles. And at this point, it assembled successfully. There's no errors. We now have a program that has kind of a layout of what we want to do, but doesn't actually do anything. But at this point, it's probably a good time to save it. So we type in save, and we're going to use the up arrow key. And that comment that we put in the very first line, which had @pic.s, it'll automatically look at that and save it with that name. So now if we type in $$ to look at the disk directory, we can see pic.s towards the bottom of our directory there. And it stores its source code as a sequential file. Now, if you wanted to look at the source code without line numbers, and I do that quite a bit, we can just type print instead. And now you get a nice printout of just your source code without the editor line numbers. So we ran the ASM command before, and it assembled, and it basically just did a syntax check and made sure our code was in good working order. So we type in ASM, this will actually assemble the code and create object output and store it at $3000. So we can do that, and it is there. And if we type in sys $3000, our program would run. And of course, it does nothing. But another interesting feature that this assembler has is the ability to just type in RUN as if it's a basic program to run it. And what that does is instead it assembles the code and then immediately runs it. But just a key point, it's not assembling to 3000. What it actually does is it takes the source code part of memory that we have, that 0800 to 2FFF, figures out where a good spot in there it could fit, and it assembles it there and then runs it. So it's really convenient. So we're just going to use the run command going forward to run our program. So let's take a look at what we have again. So looking at these routines, you might think that we're going to start at the top and then work our way down and just implement all those routines. That's actually not what we're going to do. I like to implement the routines that are simplest first and that I can immediately test. And the simplest routine in there is wait key. So we're going to create the wait key routine. Okay. So first thing we want to do is we want to get rid of our to-do list item and we're going to implement it. So let's list our program now so we can see our source numbers. We're going to remove the wait key line in 180. We're going to take it off of our to-do list, and then we're going to implement it. So we'll start running at line 500, and we'll do the same thing we did before. Get a little comment section. This will be wait key. And this routine is pretty simple. We're going to define an equate k.chrn, and it's going to equal FFE4. This will declare a label that gives us the address of the kernel character input routine. So we're going to create a loop by establishing a label called wait key, and we're going to JSR to k.chrin. Oops, go back up here, we made a mistake. We put a $sign in front of it. And that's going to call the kernel and check to see if a key was pressed. If a key is pressed, it loads the accumulator with a value, and we can move on. If a key has not been pressed, it's going to load the accumulator with 0, which also means that the 0 flag is set in a CPU status. This lets us use a BEQ mnemonic, branch when the status flag is 0, and we will branch to wait key. So it will wait until someone presses a key, then we can RTS, we'll get rid of that, and that'll return to the main program and continue on. So we can just run it, and we can see it's waiting for a key. We press a key, and voila, wait key has run. So once again, we will save our program as we are making some progress here. So now let's move on to the Config VIC routine. This routine is actually going to do quite a bit. Even though it's not much code, there's quite a bit going on. So I'm going to write the code line by line and just explain what each part does. So let's take it out of the to-do list. So Config VIC is in line 160. So we'll type 160, enter to get rid of it. And we'll write this code starting at line number 1000. So once again, we'll create a little comment block here. This will be config the VIC. So there are 4 things that we want to set on the VIC chip, and we'll start at the top. So the first thing we want to do is configure the VIC chip to look at bank 1, that second 16K block of memory. You actually don't do that on the VIC chip. We're actually going to use one of the registers exposed on the complex interface adapter, number 2, to do that. And that's at location DD00. So you can see that the default value is 11, which is a 3, and that means it's at bank 0. Well, we don't want bank 0, we want bank 1. Bank 1 needs a bit pattern of 1, 0, or 2. And you'll notice I've got a column default value and desired value. Desired value is what we want to set this to. So we're going to load into our accumulator a 2. And then we're going to store that at $DD00. So the next thing you want to do is configure the VIC chip to go to bitmap graphics mode. And that's done through the register on the VIC chip exposed at $D011. So you could see the line that's in bold is the one that we want to configure to, which is the 5th bit. Default value is 1B. And if we flip that 5th bit on, the binary for that becomes 3B. So all we have to do is load into the accumulator a 3B. And we're going to store that at $D011. So now we have bitmap graphics mode on. Now we want to turn on multicolor mode, and that's done through the register at D016. And we want to set the 4th bit from a 0 to a 1. So we're going to load in the desired value of D8, and we're going to store that at $D016. Now the last thing we need to do is we want to configure where the matrix color map is going to go and which side of the 16K or 8000 byte pixel data is going to go. And again, if you look at the table there, we can see that bits 1 through 3 deal with which side of the 16K the bitmap graphics go. Because we're in a bitmap mode, the only bit that matters is bit 3. And if we set it to a 0, it's the low AK. If we set it to 1, it's the upper AK. Well, we want it to be a 1. So the desired value we want in there is a 78. So we're going to load in a 78. And we're going to store that at D018. And then we're going to type in RTS to return to subroutine. Okay, so at this point, we should be able to ASM to assemble it. Oop, and we have an error. JSR config VIC. That means I forgot to put the label in our function. So let's go back up here and fix that really quick. config VIC. All right, so let's assemble this now. It assembles correctly. Let's save this first. So now if we run our software, what do you think is going to happen? We get what looks like a blank screen. No, the program hasn't crashed. It just has nothing to show because we haven't loaded any data into memory yet. And the memory for where the bitmap is blank. So let's press run, stop, restore. We're going to choose no. And now we're back into the editor. If we do a memory dump of memory just 6,000, we'll see that indeed it is all zeros. So how do we test this routine? Well, we have a picture disk, all pictures here. So we can just load one into memory and we should at least see the pixel data. So let's do mload. This is a command to do a machine language load, and we'll pull in Tiger. It's a cool picture. And we press enter. What this command will do by default is load that into memory to where the header tells it to. And as we talked about earlier, the header tells it to bring it into memory just 6,000. Okay. And now if we do an mdump of memory just 6,000, we could see that there's data there, and that is most likely our pixel data. So if we run our program now we see the pixel data, and it's kind of black and white and kind of screwy because we haven't copied the matrix or the color memory in yet. So this looks pretty good. Now we press a key, we're still in this mode. So let's press run, stop, restore. I'm going to choose no. And I think at this point, it's safe to say the next command we want to implement is restore the VIC. So we can press a key and pop back into our assembler here. Okay, so let's take the restore VIC command off of our to-do list at line 190. So we're going to blank at 190. And we're going to list lines 1,000 forward. So we're going to do 2,000, 16 dashes. Okay, this is going to restore the VIC. And this is going to do the exact same command as config VIC, except it's going to do them in reverse. We're going to put it back to our default values. So instead of loading a 2 for DD00, we're going to load a 3 to put the VIC chip back at bank 0. So I'll just type these commands in real quickly here. And then we'll end it with RTS. All right, so let's save this, as we like to save our program every time we write a new routine, just in case something goes south. I already see a mistake right away. I forgot to put in the label for restore VIC, so we'll come right up here to line 2030, and we'll just insert a few characters, and we will type restore VIC. Okay, and we'll save this again. Then we'll use the ASM command to make sure it assembles. If it assembles, now let's see how lucky we get when we run it. There's our tiger. We're going to press a key, and now we're back at the assembler. So we're looking pretty good. So let's take a look at our to-do list. We're down to just 2 functions now. Well, clearly the most important one we want to do is copy colors. And what that's going to do is copy the color memory from where it loaded into where it needs to be. So let's put that in, I think line 3000 looks like a good spot. So let's first remove it from our to-do list up here. So we'll get rid of line 170 or copy colors. And again, we'll list 2000 on, and we'll do it at 3000. We're going to create some variables so this program can be easily reconfigured to be able to be used in different memory configurations. So let's start with VIC bank. We're going to make an equate, and we're going to equate this to 1 for the VIC bank. So in the future, if we wanted to use a different bank, it should be pretty easy to just adjust this number to use a different bank. Okay, then we're going to talk about VIC base. This is the base memory address, right? And we're going to make this equal hex address 4000, which is 16,384 in decimal, right? 16K. And we're going to multiply it by the VIC bank. Right? So for VIC bank 0, that's memory to 0. For VIC bank 1, that's what we're going to use. It's 16,384. That's the starting address. So that'll make life easier again later on. Now the bitmap is going to be the VIC base, right? So it's going to be $4000, plus we want to add 8K to it because we're using the second half of the VIC bank. So we'll just add in hex 2000. All right. Matrix, this is that color matrix memory. Well, this is going to be the VIC base, right? So that's that 16,384, that $4000 address. And we want to add in 7K to it, which is 1C00. Now, it seems like I know these numbers off the top of my head, but I don't. And if you're not sure what 7K is in hex, well, you can use the nifty calculator command that's built into the laser assembler. So let's exit out of here for a moment by pressing enter a few times. And if I were to calculate the number 7168, or let's even go backwards. Let's say I want to calculate 1024 times 7 to get 7K. By running that command, it'll do the math, and you'll get 7168, but it'll also show you the answers in hex, and in decimal, and in octal. So that's super useful. And that's where I get that 1C00 here in line 3060. So let's continue on. We wanted to establish a color mem is at memory address D800. That memory just never changes, but we're just going to make a variable for it so our code is more readable. Let's take a look at what we have so far. So we start running at 3500. So we'll start with copy colors. This is the actual routine that's going to do the logic. We're going to use the X register to iterate, move the color memory that was loaded into the matrix memory. All right, and this is going to be a loop. With an 8-bit X register, we can't loop 1,000 times. Instead, we will loop 250 times and copy 4 bytes of memory at a time to get our 1,000 bytes copied. So it's very simple. We load bitmap plus 8,000 indexed by X. That's going to load in the first byte of the color matrix memory that's sitting right behind the bitmap data in memory. And then we're going to store it at matrix memory indexed by X. So now if we do that 250 times, we get memory addresses 0 through 250 for the matrix memory copied. But we also want to do it now for the second 250. So we're going to load bitmap plus 8250 by X and store that at matrix plus 250 by X. And then as you can imagine, we're going to do, oops, this is supposed to be 250. We're going to load this by 8500, store it in matrix plus 500, load bitmap plus 8750, and then store that in matrix plus 750. So that's going to move the 1,000 bytes of memory from the matrix memory that was loaded when we loaded the file in to where it belongs at address 5C00. Now we just have to do the same thing for the color memory. So this is pretty straightforward. We're going to load bitmap plus 9,000, because remember, the color memory is behind the matrix memory in the file format, and we're going to store that at color mem comma X. Then just like before, we're going to do another 3 iterations of it, where we load in the knife 250 by X, store it in color mem plus 250 by X. We're going to load bitmap plus 9500 by X, store that in color memory by X. And I could see a couple bugs here from rushing here. Okay, load bitmap plus 9750 comma X, store that in color mem plus 750 comma X. Okay, that's the main part of the loop. And then we increment X to go to the next one. Now we're going to compare X with 250 to see if we've completed our loop. If it equals 250, it's going to set the 0 flag. And if it's not the 0 flag, we'll just go back up and do another loop until we get to 250. And then the very last thing we need to load is the background color. And that's at bitmap plus 10,000. And we're going to store that into the screen color register at DO21. And then we're going to return from subroutine. Now let's see if we got everything correct. So we're going to type ASM to assemble it. Oops, we have a mistake. I spelled bitmap nitmap on line 3580. So let's take a look at that. Oops, list 3580. And here we're going to spell bitmap correctly this time. And let's assemble this again. Clear the screen here. And it looks like it assembled correctly. Well, before we run this, we want to save it to ensure if anything goes south, we don't lose our source code and all the work we've just done. And if all goes well, we should see our tiger with all of its color. So now we have successfully loaded the graphic into memory. Now there's going to be one small problem. When I press a key here, it leaves us in this kind of white background. So that's not going to really work for us. I mean, it's technically correct, but remember the background color was one of the parts of the image. So we're going to just press run stop restore, hit no. And I want to restore the background color to at least this color in the assembler. So we could take a look at the background of the screen by looking at memory address D021. And in there we see FB. Now color memory is interesting because only the low 4 bits matter. So we need to figure out what the low 4 bits of FB are. So we're going to calculate FB. The only values we care about are these here. So we're going to go 1, 2, 3, 4, and that's what we want to see. So we want to see what is, and it's 0B, okay? So if we put a 0B here, the color should remain the same. And if I put something else here, it'll change. That's probably not the right color, but oops. So run stop restore now. So let's look for that routine, restore VIC, and we're going to add a command at the very end to restore the screen color. So restore VIC, where is it? There it is. So let's add a line of code at 2105. We're going to load in that 0B. Then we're going to, at 21.6, store it in D021 so we can get our screen color back. So let's just run this. There's our tiger. Press a key, and now we get our screen back. Fantastic. So let's save our work so far. Let's verify that our existing code works correctly. Let's load, I don't know, burger. I love a good juicy burger. So I'm going to load this in and give it a run. All right, run this, and voila, we have a burger. And voila, our code works correctly. Excellent. At this point, I'm going to save the code. It's actually getting quite late here, and I'm going to return. I'm going to return tomorrow to continue, but for you, it's going to be about 6 seconds from now. So let's save this, and let's jump in time till tomorrow. All right, it's the next day. I'm going to load my Laser Genius assembler, and we're going to continue from where we left off yesterday. We're going to choose the high memory version of the assembler. We're going to configure the source code memory to use 0800 to 2FFF. We're going to change the disk to our pictures disk with our source code. We're going to load it into memory, and then we're going to continue. So there's one thing I don't quite like about how the source code files are saved and load in Laser Genius. When you load them back in, it automatically renumbers your program starting at 10 by 10s. So if you had any kind of pattern for line numbers, they're gone. Not a big deal, but it's I kind of wish I preserved it. So let's take a look at what we need to do next. Well, our to-do function now has just one line left, load file. So we don't even need the to-do section anymore. So we can use the delete command to delete lines 120 through 150. Am I sure? Sure. Now they're gone. And then if we look towards the bottom of our program, we could start writing in the routine to load a file from disk. And we'll start this at line 1000. So let's turn auto numbering on, start at 1000, create our separator. This is going to be a load file. So the way that we're going to load a file involves 4 kernel calls. We also need to create a buffer to store the file name, and then a 1 byte of memory to store the length of the file name. So let's start with the buffer for the file name. So we're going to create a label called fname, and we're going to make it a byte, and we're going to create it with a file name. We'll put tiger in there for now, and we'll just give it some extra space, like, I don't know, 10 extra characters. 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, that's going to be useful later on. We also want to create a label for bytes for file size, and we're going to store 1 byte in here. Tiger is 5 characters long, so we're going to put a 5 there. All right, so now let's create some more labels. We're going to create a label called device, and we're going to assign it to a memory address in 0page $BA. This memory address stores, oops, I forgot to put an equal here. This memory address stores the value of the last drive, or last device rather, used to load a program. Well, since you've loaded our program off of a device, whether it's drive 8, 9, 10, 11, or 30, that value will be there. So we can use that as our starting point. This way our program will just work with whatever disk is in the last drive used. So now we're going to create some equates for the kernel calls that we're going to use. We're going to be using, as you can see in this graphic, set to LFS, which is at $FFBA. Oops, I keep forgetting these equal signs here. So I put an equal there. We're going to use set NAM, which is at FFBD. That's actually set NAM. Set MSG, which is at FF90. And last, we're going to use load, which is at FFD5. with all of this in place, we could start our load file routine. And the very first thing we're going to do is turn off kernel messages. Kernel messages are those little messages you see like when you load a file that says like searching for the file name, loading. We don't really want our users to see that, so we're going to turn that off. Turn these off by loading a 0 into the accumulator and JSRing to set to MSG. That routine will turn off kernel messages. So with that out of the way, we need to prepare to call set LFS, set the file number of the device and the secondary address. So let's start real simple here. We're going to load it to the accumulator, a 1, because we're going to use file number 1 to open it. It's a good place to start. We're going to load into X whatever is at memory address device. At my machine, it's pretty much always going to be drive 8. We're going to load into the Y index register a 1. And that is called a secondary address. When you choose a 1, that's what we're going to use, it's going to load the file into memory as specified by the 2-byte header of the file, which in our case will always be 6000, hex 6000. And then from here, we just JSR set LFS. So now the kernel knows the file we're going to use, the device number we're going to use, and how we want to load into memory. Now we need to tell the kernel about the file name that we want to load. So first we need to load into the accumulator the size of the file name, and that's just at memory address F size. So an LDF size will go to that memory address, and which we have a 5 hard-coded, a load of 5 into the accumulator. Pretty straightforward. So now we need to load into the X and Y register the address of the file name, and it's very simple. We load into X the low value of F name, and you use the less than to indicate the low value. All right, and then we're going to load into Y the high value of the memory address of F name. And then we call JSR set name. And now the kernel has the file name ready for our action. And the action, of course, for us is going to be load. So before we call load, we need to load it to the accumulator a 0. That tells load we're going to do a load. If you load a 1, it verifies the file. Well, that's kind of useless to us. We want to actually load it into memory. And that's pretty much all we need to do. We just call JSR load. Everything else is ready to go. At this point, the kernel is going to load the file into memory. Now we want to turn the kernel messages back on. So we want to load into the accumulator, and we're going to use a bit pattern for this, because %. And you need to set bits 6 and 7 to 1 to turn the messages back on, and the other 6 can be 0. All right, and then here we just call set MSG, and then we do RTS. And that should be it. So does our code assemble? It does assemble. We are going to save it. And if all goes well, it will load the tiger picture off the disk and display it in memory. Let's give this a shot. All right, seems to be loading. There's our tiger. We'll press a key and we're back. Fantastic, our load command works. Let's try a different file. Let's try Ferrari. So let's go take a look at our new code, which is down here. Here we go. And instead of tiger, we're going to load in Ferrari. So I'll type in Ferrari. Save that. And this file name there is 7 characters. And now let's run our program and see if our Ferrari loads. Wow, it's pretty cool. That's a nice looking Ferrari. Man, I wish I could draw like this. Actually, I wish I could draw at all, but that is really nice looking. All right, now we're back at our source code here. So where do we go from here? I think an interesting place we can go to next is creating an application that uses our load and display routine here in a slideshow. So let's do that. Let's create a program that takes 4 or 5 files on a disk and just shows them one at a time, and we can press spacebar to see each one of them. So a good place to start with this is by forking this into a new file. So instead of pick.s, we're going to call this slideshow.s. This block of code here, we're going to treat like a subroutine now, and we're just going to call it KOALA, because now we will be able to call it from somewhere else. Now, since we're going to be treating this like a subroutine, we need to kind of jump ahead in the code. So we're going to add a new line of code here at 25 that's going to jump ahead to a routine that we're going to write called slideshow. So now when a program starts, it jumps down to a new routine we're going to use, and then that's going to call this KOALA routine over and over again for our slideshow. All right. So let's first save our new file with save. And let's take a look towards the bottom here, and let's add some code to make a slideshow. So we'll start at line 2000, and we'll call this slideshow. We need to keep a list of the file names that we want to use in our slideshow. So let's create a label called fnames. We're going to put in a list of file names separated by a null that terminates with a null for the files that we're going to display. So we'll start with .byte, and we'll start with Ferrari, and we'll end that with a 0. We'll create another block of memory here for micro, and we'll put a 0 there. And we'll create one for the file called Sunday. And lastly, for now, we'll create one for a file called shop. And then we're going to end with a 0. That is our null terminating file name. So when we read a file name that has nothing in it, we know we're done. So how do we iterate through these file names? We're going to do it with an X register and a Y register. The X register for us is going to represent us looping through every single character starting at the memory address in fnames, which is that letter F, all the way to the end. But we're going to use the Y index to iterate through each file name. So Y will be 0 when we're at the F in Ferrari, at the M in micro, and at the S in Sunday. And we're going to use Y also to determine the length of each file name. So let's see how this is done. This should be pretty straightforward. So first we need to create a label. This is the label we're going to jump to when our program starts. Right? And the first thing we're going to do is we're going to set X to 0. So we're going to load the X index register with a 0. We're going to load the Y index register with a 0. And now we're going to start a loop. All right? So we need to load into the accumulator the first character of the first file name. And we do that by loading fnames, X. So that's going to bring the F into the accumulator. If there's a 0 there, let's pretend that we're after the I and we've hit a 0. The 0 flag is set because we've loaded a 0 into the accumulator, and we can use the BEQ, the branch when the 0 flag is set, to name done. That's going to be a label we're going to write a little later when we're done reading in a name. Since we're not done reading a name and we have that F in the accumulator, we're going to store that at fname indexed by Y. And if you remember, fname was that little block of memory that we created that was like 20 spaces wide that we could store a file name into. And at this point, we want to increase Y by 1, increase X by 1, so we can move on to the next letter in the next file name. And we're going to jump back to name loop. Awesome. So now we've read through a name. So now let's get to this name done label here. This is where we jump to when a 0 is read. So the first we want to check is the Y index register a 0? That last 0 file name that you see on line 2070, if we hit that, we want to branch over to a label called all done. So we're going to branch over to all done. So the Y at this point has the length of the file's name, and we could store that in the F size variable. So we've got 7, we're going to put that in there, and we're ready to move on. So now we need to call our KOALA routine. However, we need to preserve the X and Y index registers because that's what we're using to loop through these file names. And if we just JS over to KOALA, all those routines are also going to use an X and Y, and it's just going to get all shuffled up. So we need to preserve those values, and we're going to preserve those on the stack. Now in 6502 assembly language, you can only push the accumulator and the processor status to the stack. So we have to do a little bit of shuffling here. We're going to use a TXA to transfer the X index register into the accumulator, and then we're going to push that accumulator onto the stack. We're going to transfer the Y index register to the accumulator, and then push that onto the stack. And now we can call the KOALA routine that's at the top. Image is going to load, it's going to display, user's going to hit a spacebar, it's going to come back here. Now we need to do the reverse. We need to pull off the stack the accumulator and transfer it back to the Y register. We need to pull the accumulator off the stack again and transfer that back to the X register. And now we're back where we need to be. So now we just need to increase X by 1 to go to the next character. And then we need to reset Y to 0 because now it's got to be the first character of the next file name we're going to process. And we jump back up to name loop. And then, if you remember going up before, all we need now is an all done, and that's going to RTS. And that hopefully is it. So let's type in ASM, see if our code assembles, and it does. Always save it before you run something like this. All right, let's cross our fingers and let's give it a run. Ooh, it seems to be loading the first image. Ah, there's our Ferrari. All right, so that's the first image. So let's press a key. Comes back to here. It's loading the next image in. Ah, there's micro. Very exciting. There's 2 files left. Let's move to the next one. That's a pretty delicious looking sundae, so that looks pretty good. And then we have one left called shop. Pretty neat. All right, this is looking pretty cool. Now that was our last image, and now we're back at our prompt. So our program worked quite well, I think. Let's make things interesting. You'll notice that in between each image, it brings us back to this screen. We're kind of looking at the color memory kind of overlaid on top of our text in between each image. What if we move the initialization of the VIC chip and the uninitialization of the VIC chip to the main program, and then this way, every time we called KOALA, we could see the new image loading in. I think that'd be kind of neat. So let's do that. So we're going to take line 70 out. That's JSR Config VIC. We're going to remove that. And then we're going to remove the JSR Restore VIC. And then we're going to put those routines at the very end here. So here's our slideshow. Oops, let's get a little bit further down in our code here. So I would say we can introduce a line 2075 here that does a JSR Config VIC. And we'll move the slideshow label up here. And then we'll take slideshow out of here. So now the code will start by configuring the VIC chip and then start loading the names in. And then we'll see everything go beyond that. And then all we have to do then is at the very end of it, call that cleanup routine. Let's see if I can find the end here. Here it is. So when all done, this will now do a JSR to restore VIC. And then this will RTS. All right, let's make sure that assembles correctly. Spelled everything right. We're going to save this. And let's give this a run. Oh, that's kind of cool. We can see the previous image that was there. We can see the new image actually loading into memory right on top of it. So we can visually see just how slow this 1541-inch disk drive is. Now, I suspect it's going to take a couple seconds after the image paints because it's still loading into matrix and color memory. And then when it's done, it should just plop into the screen. Pretty neat. And we'll just do one more image like this. We'll press the key here. And now we can see micro loading in, just block by block. Wow, this just highlights just how slow this disk drive is, doesn't it? And there we go. All right, I'm going to run stop restore this. I don't think we need to see these all again. So we can press no. So here we are at the end of the video, and we've covered in pretty good detail how to configure the VIC, load a KOALA image and display it, and then make a slideshow out of it. All of the code for this video is in a GitHub repository, along with the disk images. So you can either grab the disk images and bring it in your emulator and try to run it, or you can just grab the source code and maybe translate it into a modern assembler or something. As always, I just like to thank everyone for watching these videos. I can't tell you how cool it is to see so many people enjoying the same passion I have of writing software on these 40-year-old computers now, I think. Jeez, it's amazing. So again, thank you guys so much for watching, and hopefully I'll see you soon. Take care.